So, okay. Do you have any doubts in week 7 or any previous weeks?
Yeah. Hello. Am I audible, sir? Hello.
Yes, audible. Prithvi, tell me, like, I think Levin of Sam is joined.
Yeah. Here. So yeah, I had a doubt about GA6 question 7, grade assignment 6 question 7.
Okay, let me check.
So it is about the exception register exception.
Graded assignment 6, right?
Yes, sir. Yes, sir.
Okay.
EPC exception program counter register.
It's over or like
Sorry.
deadline is
Deadline was last Sunday, sir. It has been
okay.
submitted.
Question number 7, right?
Right. EPC count. EPC register.
Yeah, what's your doubt?
I think the answer should be option A and not option D. The first one should be correct instead of the last option. I mean, the last. So the thing is, from the lectures, in the lecture, professor says that the program that is currently executing meaning the one that is running when the interrupt happened. The program, the that particular program, the address of that instruction is stored on the EPC.
So
And
actually, by default, program counter will store the next instruction. Okay.
okay, okay,
So in that sense, when you save a current program counter as a EPC, when an interrupt occurs, then it will
mhm.
be the next instruction to run when going back from the interrupt, right?
Right, right. Because the instruction that is currently executing has not completed and it has been interrupted, so it should start again, right? That should be rerun in a sense.
So it's not how it works. Actually, if you see in an instruction level, when an interrupt cannot break between an instruction. Okay. So an instruction
Okay,
is an atomic thing in the sense. Okay. So an
okay,
interrupt cannot break in between an instruction, only after an instruction.
okay, okay. But in the lecture, it was mentioned that it stores the currently executing program. I looked it up on the slide. If you just give me a minute, I'll try to find that out of once again.
Yeah, maybe that would be good.
Yeah.
Okay, maybe you can continue with the others. I'll try to.
Yeah.
Um,
Okay.
I'll look to the slides. I had it saved, but I'm not getting it right now. I'll bring it up.
Yeah. Okay. So you have any other doubt, Shereen? Okay.
I had one from week 4.
Okay. Week 4.
Week 4 graded assignment for question 3.
This one.
So in that, the second option, the process remains in zombie state until its resources are reclaimed by the scheduler. When it encounters a process in zombie state, shouldn't that also be correct?
Okay. Let me see. The process will start. Yeah. Okay. Actually, the scheduler doesn't reclaim the resources. It was done by the parent process. It's not done by the scheduler process. Actually, the parent in the wait system command does these things. It calls that waking up process there from there. If you could see, scheduler doesn't changes the things. It only schedules things based on that. If you could see in the procs.c, in the wait system call, here, this is called by the parent, right? Actually, this checks whether the things is a zombie, and this reclaims the things. It's not done by the scheduler.
Okay, got it.
If you see the code of the scheduler, there is nothing to reclaim the resources. If you could also see that from the scheduler's code in main dot. I think it's also in proc.c. Yeah. This is just checking whether a thing is runnable or not. It doesn't check anything about a zombie, right?
Yes, correct.
Yeah. Any other doubts?
Week 7, there is no graded assignment.
We have released, right? Hello. Week 7, we have released today.
Oh, it's not released yet.
I think, yeah, they said, okay, we'll check once. But there will be a 7. Don't worry.
I think week 7 lectures are from NPTEL.
Yeah,
correct.
week 7 from NPTEL. Week 7, 8, 9 will be from NPTEL.
Okay. The slides
These
for
3 weeks. So these 3 weeks will not involve specifically to XV6. It will be in more general case.
And the slides like will be provided. And you can go also just as a profile. And now you can also download the slide. We'll upload in that drive if you want.
Yes, that will be useful.
Okay.
And there is one thing actually here in this. I think it's
Week 5, last one.
Yeah.
GA, I think.
There was a
PA.
Yeah, there was a problem in this question. Actually, none of these answers
Graded
were
assignment.
correct.
This one or the other one? You're looking at PA. I think
Yeah, actually, this is also wrong. And similarly, the graded assignment last question is also wrong.
Okay, yeah.
There was a problem with these questions. Actually, how this should happen is I have made a simple calculation mistake in both of the things so that the answer became that. Let me go through it once, right? How this will happen. So there is this argc, right? So there is first this argv. And what is argv? It's an array of string pointers. And it will point to the string. Okay. And we start from 0 and go till there is a argv, which means last argv of argc out of the thing will be an empty thing, right? So until then we go, and what we do is check for the length of the argc, which means the current argument. And why strlen plus 1? That's because strlen will will count only the number of characters without the trailing null value. So to hold that string, we also include that null character. That's why this strlen plus 1. And then this is for alignment. And after that, we do this repeatedly for every argument. And then to store that argc, so to store that argv pointers. So argv is a pointer, right? Array of pointers. So what we do is here, why this came to be 96 is I mistakenly substituted 16 for a size of u in 64. It should be sorry about that. Yeah, not sure why this is happening to me. So what should happen is here we should substitute 8, and then the answer would become, for this the answer would become 80. So to verify that also with the code, I actually added some print statements and how this happens. So I'll walk you along the computation of the practice assignment, how that worked. So here, when I just call a program, the shell will call the exec system call to do that, right? And I have added some print statements for doing this. So I am keeping track of the initial stack pointer in a variable x, and I am decrementing the stack pointer, and I'm printing how much it was decremented, which this is what our required value should be. So let's run this. I have a, so here you have, sorry, some util, that this is some executable, right? And this is the first argument. So I have this file in there. So instead of this util in some inner directory, I created it's in the same directory but with same number of characters. So this util will contain bin some util. So instead of that slash, I used underscore so to match the number of characters. So let's see what happens when we run this. Put this in some file1.txt, right? So is file1 without underscore? Yeah, without underscore. So when I run this, you could see this is the content in that file which is printed, because basically I copied the cat thing. So this is same as cat. So it just prints the content in that file. So what is happening here? So before pushing, the stack pointer is at 4000. So this is in hexadecimal. And then when adding argument number 0, which is this, argument number 0 is this, how many characters does it has? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there are 14 characters, and strlen plus 1, right? So the null character will be also added, and you will get x minus 15, right? So 15, it goes, so due to this line, it reduces by 15. And we align it to the nearest multiple of 16. That's why we got 16 here after alignment. And then in this loop, we add the next argument. Here the next argument has this. This is the next argument, which has 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Yeah, 19. This is 19. 19. Let me recheck. So, so there are 19 characters there, right? So there are 19 characters, and the size will be 7 plus 1, which is 12. No, 20. 19 plus 1, 20. So that you get x minus 36. That will get subtracted. And after aligning, you will get 48 because that's the nearest multiple of 16. And then all the arguments are pushed. And now we have to push the argument pointers. So each argument is a string, and argument pointers are pointers to that string. So you can consider that like an array of pointers. argv is actually an array of pointers to the string. And to do that, we need for each pointer so there are 2 pointers here, and here if you see why we need arg plus c plus 1. So the last should be empty, right? To mark the end of the thing, so that the last will be empty. So since the number of arguments is 2, we'll include 3, and in that 3 you have okay.
Maybe you can go to the district. I'm telling you.
Okay, let me finish this. So again, you will have 16 into 3, which is 48. No, 16 into 3, which is yeah, 42. I think, yeah. Really, no, 6. It's not 16. Yeah, I'm miscalculating again. So this is 8, and 8 into 3, which is 24. So 48 plus 24 is 72. Okay, 8 into 3 because of that, and you get 72. So then aligning it to the nearest multiple of 16, which is 80, then we have this. So the answer should be x minus 80 here. And similarly, the answer here will also change here. So here it would be, in this case, cat file1.txt. If we could see, it is, yeah, it's working, right? So stack pointer is at 4000, and since this has only 4 things, you will minus 4 because 3 plus 1 is 11, and then after alignment you will get x minus 16, and then adding the next thing, here you have 9 characters. So this is 9 characters, and it will add 10 due to the null string, null character, and you will get x minus 26. After alignment, it will become x minus 32. Since there are 2 arguments, we will add 3 pointers, and that pointers will take 3 into 8, which is 24, and 32 minus 20 minus 32 minus 24, which is 56. and you get this after alignment. So the answer of that graded assignment should be -64. So I was taking, while preparing this, I was taking into account the size of the pointer, this thing as 16, but it's not 16, it's 8. Okay, this is that.
And why is 1 added to ARGC?
So let me tell you. Oh, here. Where is the code? Here. This is where what you're asking, right?
Yes.
So because now if you see, we are starting from here in the loop. Where's the loop? Yeah, here in the loop, ARGC is starting from 0, right? So now what we do, we check this actually. So argv, the third argument of argv will third index, which means 0, 1, 2. So there are 2 arguments. So the argv of 2 will point to the null pointer. It will be a null pointer to mark the end of the argument array. So in that case, the argc will go up to 2 here, right? So 0, 1, and 2, right? Let me check. So here, argc starts from 0, checks that, and it will have the first thing, and argc of 1 will have the second one, and after incrementing to 2, it will have, okay, let me check. After incrementing to 2, it will have this thing, and it breaks out of this loop. Okay.
In that for loop, what is the condition that it is checking for before exiting?
This, so it just checks whether it's the pointer is not a null pointer or not. So usually the argv the last thing will have a null pointer in the argv. So there will be arguments. So the arguments are strings, right? So strings will be a character array, which means argv will have the pointer to the first character in that character array. Okay. Imagine it as like a 2D list, 2D array. So the first thing will be a pointer to that, right? And here to mark the end of the string, argc of 2 should be 0, null pointer in that case, to mark that end of the string, end of the arguments. And so it's added here. So it will be 0, checks, goes, and 1 checks, goes, and then only when it becomes 2, it breaks out.
So that loop is executed 2 times actually.
Yeah, it's executed 2 times, and it will become 2. Okay, yeah, it has become 2, right? So why we need this is the index, the last index we are at is 2, but the size of that array is 3, right? So that's why this +1 is coming. So we need to allocate 3 spaces, right? 0 for 0, 1, and 2. We need to allocate that, come down 3 steps. The stack pointer should come down 3 steps, right? That's why that argc +1 is here. So the last index, this loop will end when argc become 2, because the argv of argc has the null pointer. But our this stack pointer should also come below that null pointer, right?
Yes.
So that's why we are having this. So there are 3 elements in that argv where the last character, where the last thing will be a null pointer to mark the end of the thing. end of the argv list. So it's just like a character, null character at the end of the string to mark that, we use that. So that's why that +1, similar to this sternlearn +1. Similar to that sternlearn +1, we have this argc +1. Because RC will have the number of elements there, a number of elements in the sense that non-null elements, but the actual size should include that null pointer also, right? That's right. Okay, so that's how this happens. And actually, I think someone asked about, yeah, I think it's you only, Pradeep, about printing the values of the registers, right? You could actually go and modify and add print statements along the code to check what are the things that are there. So then if any context switch occurs, you can see when context switch is happening and things like that.
Okay, yeah. That was my question, I think, in the earlier week.
Yeah. You can actually include the print statements in any part of the kernel to see where that occurs.
Okay.
So this is an example of things that just done behind the exec system call. You could also tweak the code in such a way that it could print the statements of how things working in the back. So any other questions?
Yeah, I just looked at the things I was talking about regarding the EPC. Can you take a
Yeah.
look at the chat box? I have put in those references in the chat box. So
Okay.
firstly, in week 1, it was mentioned on the slides. Okay, yeah, you got disconnected. So the first message is, let me just put that once again. So
Okay.
yeah, this was the first message that I put in. We in week 1 slides, it was mentioned that the current program counter is stored in EPC. That is
Okay.
slide week 1 slide page 29. And a similar question was also asked on the graded assignment 1, which register stores the correct program.
Yeah, this program counter, EPC stores the current program counter, but the program counter itself stores the next instruction.
Yeah, now for that, that is a architecture specific thing. In Wikipedia, it says not all. So it depends, right? What a program counter stores. Wikipedia says that usually it is incremented after fetching an instruction, and that means it holds the instruction of the address of the next instruction. But in some processors, the incrementation precedes the fetch. That is, it will store the instruction that is currently being executed. So I found a website that was referring to the RISC-V registers specifically. I have put it on the chat box. There it says that the program counter PC register stores the address of the current instruction. So that might be a RISC-V specific thing.
So let me check this.
I looked at the XV6 book. It doesn't specify anything in this regard. It doesn't specify. I mean, the XV6 book does not mention whether the PC stores the current instruction or the next instruction. But the other website that I shared the link to, that mentions that RISC-V stores the current instruction in the PC, in the PC register.
But generally, like program counter, like it stored the
Let us check that also in case of XV6. No, RISC-V.
RISC-V, yes, we have to look at in case of RISC-V. I mean, in general, it usually it does store the next one. That is correct, but it is not always the case. There are some architecture, some exceptions. As a matter of fact, Wikipedia also mentions that in ARM7, so it also says that in some processors, the program counter points some distance beyond the current instruction. For example, in ARM7. So
in the lectures, I think like
yes, sir.
In the lectures, like in EPSC, like stored next instruction. If you saw the lectures,
Was
it
it
directly
mentioned?
from the
Because
lectures.
I remember it being otherwise. But if you can, if you want, I can rewatch the lectures once again.
Yeah,
Yeah,
So,
that would be
we'll
good.
also check with this, what is the
Yeah,
thing about this program counter. We'll also
because
check with that and confirm it.
okay, yeah, this has to be something specific in risk 5 maybe.
And which slide, like week one slide, page 29? I did not got it.
Sorry,
Like slide number, week one slide.
week 1 slide 29.
Okay, let me see it. But
So that was talking about the program counter being stored in EPC.
okay, there are 16 slides. In the week one, right?
But okay, it's not this, the overview one. This is the introduction
Okay.
overview. I think this was also part of week 1.
Okay.
Yeah, second statement of this. It stores the current program counter in register EPC.
Current counter.
Yeah, this means the program, it stores the value of current program counter, but not the current instruction, right?
Correct.
Right. Okay,
It's not the program counter, not the current instruction. So it will be
but
like
my
next
point here
instruction.
is that the program counter itself stores the address of the current instruction. If
Yeah,
you look at
that's
that
what.
XV6,
Yeah, that's what we need to check and confirm. According to our
yeah.
knowledge, it was the next instruction, and we'll check that.
Okay, sir. I'll also take a look at it. Maybe I'll raise it on
Yeah.
discourse. We can have a
Yeah.
final resolution there.
Yeah.
Also, I think the mechanism is also detailed on the XV6 book, and there it mentions the register being called SEPC. It's not just called EPC. There is an S in front of it. I don't know what that stands for though. So if you can, if you are going to take a look at it, can you? It will be helpful if you also explain that part from the book, the XV6 book.
Okay, we'll see that book also, and we'll
Okay,
maybe
sir.
we'll
And
discuss in
I'll
the discourse or next session. That
yeah
will be good. But generally,
yeah
like a program counter means like it will start the
next
next.
instruction.
Yeah, so I think like in the if you
Right.
saw in the microcontroller microprocessor, I think you have a
Yes, sir.
detail
Yeah.
here. So program counter means like it start the next instruction.
Yes, generally that would be the case, but it is not always the case. So I just want to get that portion clarified, whether in disk 5 it stores the current one or the next one.
Okay, maybe like we'll go through like 1 second and we'll get back to you
Sure,
in
sir.
the
Sure.
discourse or next session.
And maybe I'll raise a thread on discourse myself. After today, maybe tomorrow I'll create a thread, and there you can post that. I'll also post the references I've shared today.
Okay. And like quiz one result you got it, right? Or
No, sir, not really. I hard reloaded my dashboard. I think around 30 minutes ago, nothing has come up. Even now, yeah, nothing is here. So, I mean, I've calculated the marks, but nothing has been pushed to the dashboard yet.
okay. And
Chedian, have you seen the marks yourself?
No, it's not.
Yeah, it's not here.
and week 7 is like you have released, so you can check out.
It's week 7 assignment is now visible.
Yeah, no, it's
Will we be doing any coding for any new system card or something?
Yeah, we can do that. Let me share my screen. Okay, so let me revert these changes that I have done here. Okay. So let's go through it. So we'll see how a system calls are first implemented. So what kind of system call we can make? Like, so system call usually does something that to return any value from the kernel to the user process. So that's how system call work. So let's look through some of the system calls here. So you can see. So these are the system calls that are present here, and these functions, the sys functions are defined in this yeah, not here. Sys functions are defined in. Yeah, here some of the functions, this is write, sys close, these things are written, right? You can see how that are written, and let's look at the different system calls that are available here. Maybe
Could you zoom into the code, please? Hello.
Yeah, like 45 minutes. That we...
Okay. Subhendu sir, I just looked up the official RISC-V manual. So
Okay.
in that, I shared the link to that as well. Page 13 of that manual explicitly mentions that the program counter PC holds the address of the current instruction.
Okay. Okay. Maybe like
I've shared the URL. You can take a look at it later. Page
okay.
13.
Okay. 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 Then we'll like discuss among the team and we'll
Yes.
get back to you.
Okay. Okay. Sure.
so. My network is. Okay. So let's check this system call. So before creating a system call, we'll check
Could you zoom
how.
into the code, please?
Yeah.
In
there
general,
is-
when you open up CodeSpace on GitHub within your browser, the font size is too small to comprehend the code as such. We can look at it, but yeah, it becomes difficult to read it.
Okay. Is it fine now?
Yeah, now it's fine. Now it's fine.
So okay. So let's take this uptime or this get PID system call. So get PID system call returns PID, right? So let's see where it is defined, and you can see that in the syscall.c get PID will okay. Where it is in the proc.c, I think. Search here. What happened? Oh, I'm doing a general search. Let me check. This is the syscall.c. We are loading that. You should be able to search here, right? You see this? Or is it without underscore or something? Yeah. So there is a get PID function and a sys get PID function, and the sys functions correspond to the actual system call Usually this is functions call the PID function in order to do that. Okay, so let's see how the PID function is defined here. Here, what's that?
Wait 2 minutes, just we are accepting.
Okay, I think now there won't be any interruptions. Yeah. So we are seeing this getPID function, and this each system calls, if you see, it will return some number, right? Fork will return some number. It returns and you win 64, and tests this number. Am I audible? Oh, am I audible, right?
Yes, yes.
Okay, so that is this number. Okay, so now let's see how we can build a simple system call to get the size of the free memory. So if you remember, the free memory is what is a free memory? When we use a calloc, we will see that this there is a free range. This this run struct, which will have the all the it's a free list. If you see, yeah, this free list is there, right? This struct and free list is the instance of that struct, which will have all the free memory blocks linked to each other, right? So that's how we get the all the when we allocate, we get pop one item from that free list, and when we free, we include that page to the free list, right? This is how things work. So if we could access this free list from this struct, if we could uh, get that from here using this KMM, right? KMM.freelist. if we could iterate over that till null and count how many blocks is there, then we know how many free blocks are available, right? Could you get that idea? So what we are going to do is add a function here in this calloc, which will return the number of things. So we'll use uint 64 type as a return and get free memory, or just simple get free mem. Okay. Still this don't accept any arguments, and here for uint 64, yeah, we have types. Okay, that's fine. So here we'll use that kmem dot free list. So this is a free list, right? So we use another pointer to check the current. We are going to traverse through. It's kind of a linked list, right? So we are going to traverse through that list until the next becomes 0. Next becomes null, right? Null pointer. So how are we going to do that? We'll initialize a pointer. What pointer we should initialize? Run pointer, because free list is a run of struct run, right? The same thing. So we'll also initialize that thing here, a run pointer. Now we set r is equal to kmem m. It's kmem, right? Kmem. Kmem dot free list. Now we set we need a count, right? We are going to count how many pages are there in the free list. So we need a uint64 count is equal to, let's start with, so we can start it with 1, because since the list is not empty, we'll count that. So now it's a 1 page, and we'll repeat this. When current free list, this r is not null, we'll increment 1, right? I mean, I think we should be doing this. Let's check that. Yeah, while r is not equal to, it's just while r is enough, right? While r count plus plus. So now we got the number of pages, and we should also be incrementing r is equal to r dot next. So this goes on, right? When that next becomes null, we are going to stop it. So we'll count the number of pages. Then after that, what we are going to return? We now counted the number of pages that are in the free list. So the total free memory is the page size into the count. So we'll return count times page size. Right. Hope this is clear. Is this okay? Any doubts?
Yes.
Yeah. So now we have implemented this function. Now we have to create a sys function for this to do that. So if you do that, let's set sys. If you see, every function will have a sys function associated with it, and we'll also have a sys function for our this thing, which is we'll name it sys get free mem, or we'll just name it like this for simplicity. Free mem void, and we'll return same as this. We just return the out of our original function, which is this, our free mem function. Return free mem. Okay. Now that we have implemented this sys function, we can add that to the syscall.h. So we have to define a number for our system call. So this is just the number, not a function. So you see the capital sys. Our system call number is 22. And then we make changes in the syscall.c, adding that here. So since our function is defined in an external file, we'll use this external 64 sys free mem void. Okay. And now we should add this also at the index of 22. We have added it as this side, this thing. Yeah, this one we'll add. This is free. Thing we have in, did we include that syscall.h? Yeah, then okay. Then now this kernel part in the implementing the system call is done. Now we have to go to the user part. So in the user part, there is this file called uses.pl. This is what creates the eCall instruction calling with that syscall number, right? That's what does that. Taking from the syscall.h, which we added the system call number. And yeah, so we'll add an entry for free mem also. Okay. So that it will be substituted, right? The number will be substituted. So okay, this part is done. And now what we do, we create a user program that calls our system call, right? So since this is a system call, some user program should be calling that, right? So we use this. I'll rename this to get free mem. So now this is a user program that just will call our system call and do the things, right? So here in this main, I'm just going to print the output of that system call. So how do you know the system call? Since we define that in the uses.pl, this is our system call, free mem. We are going to call that function on the user side. Where is that? Yeah, here. This user program is going to call our system call. So printf is defined in user.h. System calls, yeah, maybe you need to register that system call here also. Yeah, and printf is also defined here, so we'll add that here also. User.h, so that free mem will be available to us. Okay. Where's
Here done. Here also done. Where is it? Yeah, we are in this part, right? So now we have the we'll print. We are going to print that value. The memory. So the page size is in bytes, right? Usually it's in bytes. The memory size in bytes. So this will print the whole memory in bytes. Values percentage U. Maybe we could also add something like, okay, we'll do one thing. We'll use that 64 ms equal to 3 mem, and we print in both bytes and megabytes that case. So in bytes it will be just U, and just do that bytes. In bracket it will be 2 megabytes into that MB. This, and we should be doing mem, comma. So mem is in bytes, so mem by 1024 converts it to KB, and then 1,000. This will be MB, right? Okay, we'll add a next line also. Oh yeah, pretty much everything is covered. So to include that user program, we'll modify the make file. So add that user program here. Just get free mem. Okay, that's fine. Yeah. So I think pretty much everything is covered. Let's try. Oh, make you. Virus. Routine. Okay, let's try this. Get free mem. Oh, oh wait a sec. Doesn't printing anything. Let me check. Printf, right? Printf should be printing these numbers, right? Oh, it just prints slash. Let me try again. We'll I'm just printing something. You. So, oh, I think U is not suitable in this. You should use D, I think. I'm not sure why it's not. It should be using. Let's check the printf also. Send uses. Printf is there, right? Printf is not here. Let's check. Oh, printf is here, right? pnewlib.c. Let's check the actual printf is in here. It supports printer. DL. Okay, it doesn't support U in here, it seems. So we'll use D to print that. Okay. Yeah, U is only supported in normal things. So we'll use D here instead of U. Okay. Now it's not needed. Yeah, we got the free memory now. Okay.
Okay.
So one more thing we can do. I am calling a shell inside a shell so that now we have one more shell inside the process, right? So now the free memory should be reduced, right? What happened? It failed. Yeah. Now you see exactly one page sizes reduced. Okay, let's see what happened. Yeah. See the size is reduced, right? Now if you run that get free mem, I think this is when I press arrow keys, it's behaving differently. That's why it's, let me do this. Yeah, now let's try. Yeah, now this is the same memory. So this free memory, since we are calling it from another process, so this get free memory is also an user process, right? So when we are calling it from that process, so that process and another, this is not the free memory when we are in the shell. Okay, it's a free memory when we are inside that process that we should be taken care of. So since this system call is not only limited to this user process, it can be called from any user process. Okay, so we'll move into another shell inside a shell. Let's try. Now the size is reducing, right? You can see that. So let's come out of one shell. So we come, I think we came out of one shell. No, we didn't came out. Now we came out. Now it's back to this point, 1.12. So we freed that shell, right? Inside, we came out of one shell. Again, I came out of another shell. And let's try. Now I am back to my original shell with this thing. So if you can get how this works, right?
Yes. And do you know how to use the QEMU monitor?
QEMU monitor.
If you
I'm
press
not sure.
Control A and C.
Oh, I'm not sure what is this.
So I was thinking, does this show the current value of the register?
I think there is a debugging option is also available. I'm not sure how to use this.
Okay.
It's having some options. Not sure how to use this. But actually, QEMU is an emulator, so it kind of has many options to see emulate different kinds of systems. So it will have more options than it might support to this XV6 OS. But I'm not sure how to use these options. But you get the idea of how to implement this thing, right? System call. Making
Yes, got it. Yeah.
That's the main key takeaway here. So using system call, we can call some function inside the kernel from the user. We have to define that function in the user and the corresponding system call in the kernel, and it will go to the kernel, fetch that value, come back to the user. So when calling that system call, a trap will occur. So we'll do one thing. So there's this, we saw the trap things, right? Thing handles the traps, trampoline, and it will go to the, yeah, here. Yeah, so in it. So where is that user trap red function? Where is that? User trap red, user trap function. It's in kernel trap.c. Trap.c. Yeah. So this is actually what handles the things, right? If it's a system call, and it will. Okay. Let me check. Is this? So there is some interesting things about EPCs going on +4. Okay. Okay. So now, not sure. I think about the exception program counter, we may need to check something about what it points to. So we'll come back to it later. And here, when some system call, yeah, this thing, right? Actually, this syscall function calls the system call, right? We saw it defined here. This is call function. Here we can make a print statement printing the system call number, right? So that we get from that trap frame, we'll have the system call number, and we call that system call. So here we can check the system call number. Now if we recompile this, then I call the system calls. You can see many system calls are called between things, and you can see what are the system calls that been called using that number. So now let's so then I think the first thing is 5 is called and 1 is called. So we'll look at that. So let me call this function, which is get free mem. Let's see what is called. So many things. So why the 16 is called while printing every character is the writing goes through the system call, right? Console.write. It writes using that write system call to the standard out. So that's why while printing every character, the system call 16 has been called, and that system call is the syscall function called. We are in the syscall, right? The 16, I think it's yeah, right. So that's why the 16 is called. Whenever you are writing something into the console, that system call is written, and we don't want to see that system call anymore. So we'll do one thing here: the print statement when only when syscall is not equal to the number is not equal to 16. We'll print that. Right. Now let's. Now we get some reduced number of system calls. Okay, now let's see, get free mem. Yeah, we got that, and the last system call that was called is 22, which is our system call. You can see multiple system calls that has been called, which is 5, which is read, since it read these many values, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Got many 5s there. And 12, I'm not sure about the system call, but it's being called somewhere. And 7 is exec. Yeah, when we ran the get free mem, the shell calls the exec system call to create the sub process for this user process, right? For the get free mem, it should get called that. And this 3, which is wait system call. Yeah, so actually this function is got executed by the exec, right? And the shell is waiting for it to return. So that's why the wait system call has been called. And the 12 is so I'm not sure. 7. So you can see the 7 is called and this the wait is called. Okay. And to exit. So that process is exiting, right? This kind of things you can do. Try implementing, tweaking the code, printing things. Okay. Any doubts?
Yeah. Thank you.
I think this will end the session today.
Okay, and if you have any doubt, post in the Discord, so maybe we can discuss the Discord itself.
Okay, thanks.
Okay, so thanks for joining. We can read the session.